Do you want my intro to go live into Zoom as well? Sure. Okay. All right, so are we on? All right. Hi, everyone. Welcome to an AI Squared and Agate Intellect session. So Agate Intellect runs these highly technical sessions weekly, as well as workshops, and as well as product sessions. We have a booth out there. If you want to know more, come talk to us. Regardless, without further ado, let's introduce our first speaker, Juan. He'll be speaking about fast interactive object annotation with Curve GAN. All right, GCN.
Yeah.
All right, Curve GCN. All right, thanks very much. Go.
So basically, the first three presentations here are from the same lab. So we plan to merge those three presentations together into one big presentation called AI Data Factory for AI.
Laser pointer.
What's that?
Laser pointer.
Oh, yeah, okay. That's great. Yeah, cool. So basically, machine learning is quite popular those days, right? So we have, for machine learning, we can do medical stuff, we can do auto-driving stuff, we can do machine translation, but there are two different perspectives. The first one is the model itself, but another one is label data. From my perspective, I have to say the label data is the most important thing in machine learning applications. Without this label data, you cannot train any model. So one very important label data format is called segmentation. So basically you want to segment the foreground from background. This one is quite useful in don't know about Scalar.ai. They just raised like 10 million money last month. So they're an annotation company. So their job is, so company put raw data into them and give them label data, such as segmentation. It is one example. Right. So from 3 years ago, our lab trying to develop a Toronto annotation suite. We are trying to use AI to accelerate such labeling process. So it takes 1 minute. However, use our machine learning technique, we can fast this by 10 times, right? So it's like, do you see a huge market, right? So for data annotation company, they just annotate those data manually. But if we can accelerate by 10 times, it saves them 10 times of those costs, right? This is one example of how people annotate segmentation data, but this is from very old software from PowerPoint. Basically, people need to click on those key points and to get the boundary of one object. You see, it's very time-consuming. It is like 25 times faster, but of course the boundary is still rough. Right. So here we have a series of papers. The first one is called First Interactive Object Segmentation with Curve GCN. So Jun will present that.
Is it okay to turn off this light? Because I think, where to turn off the light? Okay, anyway, so I'm Jun. So I'm going to present this paper about fast interactive object annotation with Curve GCN. It got accepted to CVPR this year. So as Juan has first mentioned, how we can do the interactive object segmentation for one image. So the pipeline we propose here is we first ask an annotator to select the bounding box of an object. In this pictures, human draw. Where is it? Anyway, human draw one bounding box around this car, and then our models are going to predict the object contours of these cars. But there's one question. How can we parameterize the object contours? You can parameterize the contours with polygon or spline curve. Like for this car, like for this white car, there are many sharp edges in this white car. So it's better to parameterize this white car with polygon. But for this car, there is more smooth edges. So it's better to parameterize this car with spline curve. So the human can select whether to parameterize it with polygon or spline curve. And then with these two informations, our models can automatically predict the object contours of a car, like here. Give this bounding box, and our models can generate the contour curves of this car. And then where comes the interactions? It comes from here. Like we cannot guarantee the models is 100% correct at any times. Even for AI models, they can always make mistakes. But how can we make, and this comes from the annotations. Suppose the models have one mistake at this point, like here, and then the humans can say, oh, this is incorrect, and I want to put this point to the correct positions. And then the models take the input of this correction informations and then regenerate its predictions. Okay, like for here, the humans say this point is incorrect, and it put this point to the correct positions, and our model can repredict the new curve. And then the question is how we can do this. So this is the model. We first have the inputs. We first take the input image, which is from the bounding box, and we resize it to a fixed size. And then we first use a CNN encoder to get the feature maps of this input image. Like for here, we get a feature map. And then we initialize the object contours with a sphere. Like we have 40 points in the equal space of the sphere. And then our model tries to predict the offset for every point, like how we can move this point to the correct positions that can match the object boundaries. And then we have different type of GCN to gradually move the points to the correct object boundaries to imitate suppose we have an initial circles, and we gradually move every point in the circles to mimic, like we gradually walk towards the actual object boundary. Okay, and the loss functions is just like we have suppose P prime is the ground truth point, and P is a predicted point. And then we can minimize because the circles is a loop, every point can be a start point of the loop. And then we have the minimum over all of the possible starting points, and we find the minimum to minimize this matching loss between the predicted curve and the ground truth curve. And then with comparison to our previous paper, because we have two papers before, which is called Polygon Recurrent Neural Network. One paper is got accepted to CVPR 2017, and the other paper, the improved version, which is called Polygon-RNN++, is got accepted to CVPR 2018. So the comparison with these two papers is that because for here we simultaneously predict every point at the same time, so it should be much faster. But in before we sequentially predict every point. Like for here, we first predict the first point, then second point, then third point. So it's much time consuming. And also we can parameterize the curve we can parameterize the boundary with curve or with polygon or spline curve. Like let's first see the first part. Like if we first compare with if we just compare with this one, the speed. So this part is the time for Polygon-RNN. We just run the first prediction. It's very 200 milliseconds. But for here, it's only we are 10 times faster than before. And for the correction part, the Polygon-RNN needs to predict the whole curve again. So it's almost the same time. But for here, we only need to predict the neighbor points. So we are much more faster than in the interaction part. And also we are much better than that because for here, we are simultaneously predict every point. So there potentially exist some interactions between every point. So we can, when I predict the first point, I can see my neighbor points, and I can know how I should move to the actual object boundary. So it potentially are much better than this kind of sequential structures. So we are much better than the Polygon-RNN in terms of the IOU, which is like the intersection over the union. This is the typical metric how we can measure the performance of the segmentation. So this is Polygon-RNN++, and this is our method. And this one is the pixel-wise segmentation mask, which is a pixel-wise segmentation method, which is I predict, because in typical way how people are doing image segmentation is like I predict the pixel labels for every, I predict the labels for every pixels. So we are compared with that method, but we are much better in the interactive sections. And this is for the human in loop. So like how we can do the human in loop. So like human, as I first said, human can first correct some points, which is incorrect, and we feed that to we feed it as the input information to another GCN, and the new GCN takes the input of the human correction and repredict the curve. And let's see one showcase of these two method comparisons. So this is the initial predictions of two methods. So this line is a curve GCN, this line is a polygon recurrent neural network. And then we can say like for the polygon recurrent neural network, the points are not uniformly spaced in the object contour. And we can say like for here, we say there's 2 points. So like you can see the correction part. So there are mistakes for these two methods, and the humans correct these two mistakes. Like I highlighted with a red circle here. Okay, so this is just the human corrections, and then let's see what the model repredicts. So this is what, like for this part, the polygon recurrent neural network will repredict every point along the trajectory. But for our curve GCN, we only repredict its neighbor points, because like for the models, it always makes mistakes on the neighborhood, and it's more reasonable to correct the information on the neighborhood. Because maybe for here, you can say in polygon recurrent neural network, actually in this bottom part is very great, but the model still needs to change it. But for here, if it's great, then we don't need to change it. Okay, so this is another advantages of our method. Like we can do local corrections, and it's much efficient for the human and much more user-friendly to do the interactions annotations. And also, let's see some. So this is one statistical comparisons with the baselines. So the x-axis is the number of clicks, like how much interaction should we interact with the real human. And then the y-axis is the IOU, the intersection over the union, the metric how to measure the performance of segmentations. So we are more efficient than the baselines. Okay, like this green and blue lines is our method, and the red and yellow lines are polygon recurrent neural network. And also, this one is the initial predictions on the initial predictions on cityscapes, which is a data set, a very typical data set to do the image segmentations. It's basically a data set on the street views. Like we need to annotate the human, the car, the motorbikes, etc. in the image. But basically, the most object in this data set is cars. So this is the comparison with human annotator. Because cityscapes is annotated with the ground truth, with the human. So this line is just actually the real ground truth data from human. But we are comparative to the real human annotations. And also the good things for our method is like it can generalize to many unseen classes. Like for here, our models are never trained on the aerial image, which is a top view of the house. But we can still fine-tune our model such that it can match the actual boundaries of the real thing of another unseen classes. And this is for the medical image. And this is the generic things, which is like for any, you just random pick some images from any like Google or something. And this is some images just from Google. So this one, the first line is like human draw one bounding boxes of the car of the like object of interest. And this is some method with, so the middle line is a method from our model prediction with several clicks. And this part is the real human. We annotated by ourselves. And you can see like it retrieves the compatible performance with real humans, but it requires very less interactions with the real human. Okay, so this is our paper. And I think the next one is another paper that we also get accepted to CVPR this year, and let's work on them.
Hello everyone, my name is Ian. So here's our another CVPR paper. It's also on interactive object annotation. So basically, it's going to use a deep level set, use the level set method for interactive segmentation, and it's combined with deep learning too for this. Okay, so let me change my slide. Oh. Okay, so first, let me introduce the task. The task is interactive instant segmentation. So we have some, it's like it takes the human interactions as input. Like we can give the object a bounding box, the bounding box of object you are going to segment, or you can give the network some extreme points. Like we can give the object we can just, if there's an object, we can give it the up, the bottom, the left part, the right part of the object, so we can tell the network which object we're going to segment. So this is the task. So we have many applications like image editing or image annotation, just demonstrated as string. So from the description, we can see the boundary performance is really important because if you have a really rough boundary, we'll need piles of effort to correct it. So then we can talk about how to formulate this task. So a straightforward way to formulate this task is to treat it as a binary classification, right? So given the RGB image, and we can use the deep CNN network to predict the foreground and background mask, and it will be in the probability, right? So then the generated result will be a heat map. So there might be some scattered island on the boundary. So if you want to correct it to like the ground truth, here, it will be a lot of effort. It's just like annotating from scratch. So then we can see boundary performance important. So recent years, there are also some other formulation, that is to treat the object segmentation task as curve detection. Like if you want to get a segmentation, you can just get the boundary of the object, right? So there are also some curve-based method like Polygon-RNN, something like that. And so let's look at more related work on curve-based method. So one traditional method is active contours. It also have the name Snake's algorithm. It's like we first have an initial contour of it. The initial contour, we can draw a polygon, like a human annotator will draw a polygon around the object you're going to segment, but not that tight. So then we can define some energy terms to make the initial curve evolve to collapse to the final boundary of the object. So that is divided in two parts. The first thing, we just draw a polygon around the object we want, and then we use some energy terms to evolve the initial curve to fit tightly to the object. So that is active contours, and there are also some recent works to combine it with deep learning, like deep active contours and deep structured active contours. But they are mostly based on polygons, so it's like the contour, how they represent the shape is polygons. Also, there are recent works from our lab, the Polygon-RNN++, and Curve DCN. They are using recurrent neural network and graph convolution network to model the moving of the points. They're similar curve-based methods. So is that a problem? So these shapes are explicitly represented by polygonal spline. So the shape so for shape, the boundary is not precise. If the points is not that dense, the boundary will not be that that precise. That will be a problem. And then is the topology. If you want to treat it as a polygon, then the topology should be fixed. It should be only one part. For example, that is many cases, like if you want to segment a car, but there's a person cause some occlusion, then the car is divided into 2 parts or even 3 parts. If you want to segment the car, then we'll need maybe 3 times. So for the case of topology, it cannot deal with multi-component objects. So here's the drawback. So here's the motivation of our level set model. So first, if we treat for the first thing we want is the boundary performance, right? So we just drop the pixel-wise classification method because it will predict really noisy heat maps. And then the next thing is compared with polygons, we want a better representation that is more flexible and can generate precise boundary and can handle the the topology changes. So there's one representation in the literature that is named the level set. So basically, we want to solve 2 tasks. So the first thing is how to represent the curve, and then the second question is how to evolve the curve, right? So the first thing is how to represent the curve. So we can, as the last figure shows, we can represent the curve with points and edges along these points. That is like polygon or splines. They are explicitly represented. But we can also use implicitly represented curve. That is, if we have a surface function that is called a level set function, if we can have a surface, then we cut it at this 0 plane, then we can also form a curve. Is that right? So you can take a look at the right figure. Here we have the surface. We can call it a function phi, and if we use the green plane, that is a zero plane to cut it here, and then we will form an object. So this is the implicit kind of representation. So in math, it can be shown this way. So here the points xy is the curve, the points on the curve. We can use the level set function phi and to make it. It's a set of points that equals to 0. So that is the way to represent the curve. But this kind of curve is a little, not that explicit. So how can we evolve the curve using this kind of representation? So for polygons, we can just move the points. If we move the points outward, then the curve will go with the points to move it forward. Move the vertices, right? If we want to evolve the curve, evolve a polygon. But how can we evolve a level set? So if we want to evolve a level set, it's just like we can just move the level set function up and down, just like as this figure shows. If we move the level set function up and down and change it, then the curve will move inward and outward. So I have many beautiful math. So here is a sum of it. It's a formula named level set equation. So basically, the left part, the C is the curve. The partial C and partial T it means how the curve moves. In how the curve evolves, like the curve C evolves in its normal direction and its normal direction with velocity v. So this is how we can use for polygons. So in level set, it is like how the level set function changes. So the partial phi and over partial t is like the v times the gradient of phi. So they are equivalent. You can prove it in math. If you're interested in, you can just take a look at it. So what is the advantages of level set? So the first 2 things are it can represent arbitrary shapes and arbitrary topology, and it will be easy to extend to higher dimension like 3D. But there are also some problems. Traditional level set methods are really noisy because similar to active contours, it's also we have an initial curve and we want to evolve the curve to fit the boundary, right? So then we need to define some energy. So for traditional level set method, the energy is defined by like local gradient. For example, if we wanted to collapse to some edges, then the edges should be, like we can use some features to describe edges, like Laplacian of Gaussian or something like that. We can use them to detect the edges and make the curve stop at the edges, right? But the features like Laplacian of Gaussian, they are really noisy. So traditional level set will also face this kind of problem, although they have really beautiful math. So how can we deal with it? That is deep learning. We can use data-driven knowledge to help the network to learn how it should evolve the curve. So this comes our deep version of level set, and so first I'll briefly talk about how we can formulate the level set energy to make it work well with deep learning, and then it's the model architecture, and then it's finally it's the pipeline of the model. So this is the level set representation. It's the curve C. It's the zero level set of the level set function. So the foreground can be represented by where phi is greater than 0, and background is where phi is smaller than 0. So for curve evolution with level sets, we can use level set equation. We can just move the level set function up and down, and the curve will change. But how can we model it in the deep neural network? So we can use an iterative update. Like we can update the initial level set for t steps. That is, given the current level set function phi subscript I, we can use the partial phi over partial t. That's like how level set will change. We can predict it, right? And then we can iteratively update it, like t steps, and then will come the final evolved contours. So let's take a detailed look at the update terms. So the update terms is actually the level set energy. So that is the rule how the curve should evolve. So it can be divided into 3 parts. The first is the motion term. That is how the level set should move, like in normal direction. What's the velocity it should move, and then it is some regularization terms. Regularization terms, like if it is a curve, then it should have some properties of curve. For example, it shouldn't be really noisy. Like it shouldn't be up and down, up and down. It shouldn't be noisy. It should be it should not be too long. Like if you want to segment a desk, it shouldn't be just hanging around. There should be some properties, like you can move it in the curvature, and also some regularization term on the level set function. It is due to numerical computation, things like that. So I'll describe them in detail. So the first term is the motion term. So the motion term determines the motion of level set evolution. So it tells at each location, if the curve lies on each location, where should it move? For example, if we want to segment the desk, but the curve actually lies outward the desk, then it should move inward. So this is the motion term. The motion term tells the curve should move inward if it is outside the object you are going to segment. So and in math, it can be formulated here. So how can we use deep learning to help this? We can use deep learning to predict the direction it's going to move. So it is indicated by the theta. It is the parameter we are going to learn. And for curvature term, so that is the regularization term. We want the curve generally to be well behaved, so it so it won't be that noisy. One of the kind of regularization is to move the curve along its normal direction. If we move the curve along its normal direction, along its curvature, then it will not be noisy, right? If you can just think about a noisy curve, and then we move it in its normal direction, then it will tend to shrink to be a line, and then will shrink to a point. So that is a regularization. But we don't want to always regularize at any part of the curve, right? For example, if we want to segment a desk, there's a sharp corner of the desk. But if you do the curvature penalization, then the sharp corner will just be wrong. It will move inward, move in the normal direction, right? But that will cause some artifacts. We don't. Sometimes the object will have some sharp boundary, so we want to selectively penalize it. So this comes the modulation function m theta. So the rest of them are the regularization. So the m theta will add something like an attention of it. So it is learned by the network. It will tell the model where should we penalize. Like if this is a line, then we should penalize it. But if it's a sharp corner, then we shouldn't do that. So it is a selectively regularization. And the next regularization term is also from the level set literature. So it's like when we computing level set in a iterative in an iterative way, there will be some numerical error will accumulate. So this term will help it to help to relieve this issue. So maybe if we look at the model, it will be better. So the input of the network is like one extreme. It's like four extreme points. The extreme points are like, here's the object. If we want to segment the grooves here, we can just tell the four red clicks, like the up, the bottom, the leftmost, and rightmost, to indicate yeah, we are going to segment the grooves out, and we propagate them into encoder CN, and there's a multi-branch CN. The first branch is so we can take a look at. We first have a level set branch. Level set branch to have a initial estimation. So for previous work, for traditional work, they're like in active contour, in level set method, this should require human to draw an initial curve, right? But with deep neural network, we can just first predict the initial contour estimation, but that will be really rough, right? So we can use level set energy to iteratively refine it, right? So the rest two branch, the motion branch, just predict the motion field that tells if the curve lies here, where should it go? Where should it move? So this is a motion term, and the modulation branch is just part of the curvature term. That is to selectively penalize the curve. It is automatically learned by the network. So given the input, we just encode it to some latent features, and we have three branches. One branch, the initial curve estimation, and two branches are the parameters we use to evolve a level set, right? Then, so we just put them together. So we evolve the initial curve with the predicted parameters, and we can get a final result. So here's the general model. And also, there's an additional branch for human correction. On the erroneous boundary, we can just drag the points onto its correct position, and then we can just encode it also into the network and repropagate the whole network, and then we can get some better result. So basically, we need a design of level set evolution, and we need to have have some energy that fit to deep learning, that works well with deep learning. And the model architecture is like that. And so the final pipeline is we first predict an initial curve and the parameters used for level set evolution. And then we evolve the initial curve to get the final result. Okay, so here are some quantitative results. Compared to current state of the art, we have better performance. Like on IOU is the intersection over union. But for interactive segmentation, I think we need to care more about boundary performance. That's the F score. And we can see we have significant improvements on boundary performance. And also some ablation study on the different parts. If we just directly regress the level set, it will not be that good. That is just the phi 0, the level set has zeros time step. And if we add the motion term and modulation term to evolve it, it will have some better results. And if we just use some low-level features, we'll also have some better results. There's some ablation study. So here are some qualitative results that's on cityscapes. we just use the ground truth bounding box to simulate it, can have some pretty good result. And here it's also, so the top row is ground truth and the bottom row is our model. So it looks have really tight boundary performance. And here are some more visualization. So for the left part, from left to right, it's original image and the initial estimation of the curve, and then it's the vector field, it's the motion field, and then modulation function and the final result. Because it changed in detail, it changed a lot of details. So in my if we can, I think I can zoom in. But here it shows some details like levels evolution. For example, here you can see here are some noises, and by evolving the initial curve, it can just remove the noises. And you can see here around the helmet, it also has some noises, and with level evolution, you can just remove it. So that's my part. So maybe you can see some demo by Juan.
It's very hard. Yeah, yeah, because I have to see the screen to show a demo.
Let me see if I can turn it on.
Yeah, it's fine. Good. Right, so as I said, so the whole presentation is about interactive segmentation. So to illustrate our ideas, our project, we built this demo, and we call this one a platform. So basically what we can do is, yes, first draw a bounding box. It will give us a rough curve, right? It's not accurate, but it's fine. The whole purpose is we can move this one to the right point by several clicks. Right. And you can get a very fine mask. And this one is not right because the body, we need to fix the body box a little bit. I can't see the screen actually. Oh. What's happened? Yeah, let's do it again. Right. So you first have a curve, and you can move some key points, and you can get an accurate boundary by such edges. Let's try another one. For example, this truck. Right, and again, you can fix some point to the key point. You can see you can point grab the boundary directly, right? And from that, you can run fine mask together, find accurate mask. You can see like by such pipeline, you save annotator 10 times of the annotation time. Basically, if you want to add to annotate this, we will follow a boundary and annotate the polygon. It's very time consuming. And surprisingly, our method also work on something like this. Right? And then get a very fine mask over it. Do you want me to annotate something? Just point me something. Anything is fine.
Billboard.
Which one?
The billboard on the right. Top right. Top right.
Top right.
Right.
This one?
Right there. Yeah.
The board? What is that? I can't see that.
It's a board.
A board?
Oh, there you go.
Yeah, of course you can get it. Move some point to it, grab the boundary, right, and you can run from yeah. And also our method works clustering. And this is, for example, MRI image. Right, this is very useful for the medical domain. For example, if we want to annotate this, right? It automatically get a very nice boundary. If you want it more accurate, you can run level sampling and get a accurate boundary. And one more. This one's not good. Let's try a challenging example. Yeah, for example, I want to segment the hair of this finger. Again, we can draw a bounding box. So it's not good, right? But what we can do is point it to. And it will give us a good boundary. But this part is not good, but you can still roll it. I guess this function is not working yet. Yeah. Do you want me to try something? So pick up an image and let's try something. This? Well, this one's a very hard one. Actually, it can work. Fix it. Right, maybe this point. Right. Pretty good. Some more? Sure. Medical? Which one is wrong? Well, well, it can work obviously. So the key point is like we draw a bounding box and we fix some key points, and this gives us a precise boundary, and this saves the annotator's time. So back to our title, our current presentation is using AI to accelerate the AI factor.
Is that done?
Yeah, that's everything.
We have around 5 minutes for questions. May I ask do you want the other speakers to be up here as well?
Yeah.
May I ask the other speakers to also join and take questions? No? You guys okay? All right, any questions so far?
So if you have a lot of same images, like for example flowers, is your model performing well?
So for example, flowers.
Yeah, for example, separate every flower on the field.
So basically here, our method is training on statistic those outdoor data set, but it works well on cross-domain images, for example, medical. For example, the raccoon we just annotated, and those special ones. So it's pretty robust for the cross-domain images. I believe it can work on flowers. You can try it out. So this demo is online.
It's not about flower, I'm talking about multiple objects same time.
Oh, multiple objects?
A lot.
Yeah,
grass.
So if given a multiple to crop like multiple objects, it can work on multiple objects.
So we have a similar thing with the cards. These are pretty similar to the cards, and they're next to each other. It's still, so I could say that that's kind of similar. But I think the point with the flowers is that what if they're really, really, really similar? Would the model still work? So do you have a bouquet or something in your? Okay. But follow up to that question. It seems that you do some fine tuning for between domain transfer. Now, how does that fine tuning?
No, don't need any fine tuning here.
In this case, in this model, there's no any fine tuning.
Every image works on one model.
Yes.
But it was mentioned in one of the I think you did actually.
It's in the paper. It's in one extent in the paper, but in this demo, so we have much more powerful.
So in that case, when you have trained it in one domain and you want to fine tune to the other,
yes.
What does the process look like? How much data do you need?
1% of the whole training data sets.
So it has to be at least 1% of your.
10%.
And the training data set would be the original data set, right?
So one choice is you don't need those annotated data. So you just use our current model to annotate those 10%, right? And do it online fine tuning.
So 10% is quite a bit still, like you have to go through.
Yeah, but yeah, so my point is, in our current model, it works robust on the cross-domain images, because basically it just grabs the boundary of your bounding box.
Okay, that sounds great.
So yeah, how to identify that the occlusion, so which object is in front and which the object is next to the foreground?
We have bounding box. The bounding box indicates where is the object. So if there's occlusion, so it will grab.
So I mean, if the annotation tells which one is occluded by the others, or there's no difference.
No. So
Can you do that?
One bounding box per object.
I think we can do that because like it's basically something like the annotation in index.
Yeah.
Right. So we can firstly annotate the most nearest object, and according to the depth and according to that. So this is basically how to re-annotation the full image.
So it's possible, say, we'll have the object, was occluded, and estimate the percentage, maybe 50% was covered, or
Yes.
10% is covered. It's
So
possible.
you use IOU then?
Yes.
Yeah. Okay. So they use IOU. So if it's more of the image exactly as you mentioned, like 60% of the image is this image, probably that's what it's referred to.
So like for example, is for this car, we're going to annotate this car. It's basically because this car is occluded by this car, right?
Right.
So I just draw one bounding box around this car, and you can generate like for this one.
So it will like ignore the occluded part and only segment the boundary of the object in this bounding box.
Yes. So it will focus on the foreground part.
Yeah. So for this model, it doesn't make sense to complete this shape, right? Because you want to allocate any object.
But before training though, this is I imagine this is the result of a full trained model, right?
Yes.
Before training, would you do IOU, detect the one, and then start sort of annotating further, getting better curves? Is that how it works?
No. So in this case, we have polygon annotation, right? So we just crop those images. So if it's occluded, we just take off the non-occluded part.
Okay, makes sense.
So I think for the
That's the last question.
okay. So I want to make sure I understand it correctly. So the model is actually using the deep extreme level set to do the original instant object pick first, right? And then the optimization is that. So that it costs if this is already trained, so I want to know how it is before it's trained, and then what steps to doing this. So based on we need to, because you said you need to input some of the training data sets, but I want to get one thing of that, what did it, how this data set did look like, and then get trained, and then what's the step for it.
All right. So is this a good summary? What does the original data set look like, and the steps to go to the fine tuning? Is that what it is?
Yes.
Okay.
So, I think you
If you could summarize it in 1 minute, that would be amazing.
Oh yes, so the training set is also on cityscape data set, like similar to the Polygon-RNN and curve VCN. So it's also using the curve. It's also using cityscape data set. And for training, we first use some pre-train. We first pre-train the level set branch and using some unsupervised or self-supervised method laws to define supervise like the initial level set and the evolved final result, right? So we can do the pre-training here, and then we can just jointly using the final we can just jointly train them and supervise the final result. That is the level set function at time step t, right? And we can use the binary cross entropy laws to supervise them. So do you mean that for the training or how?
So I think that adequately answers the question. But let's take it offline if you have more. We want to know more details. Please approach the speaker after the sessions. The next one.
Can we say it like
Okay, let's take a 5-minute break. Jane, which one?
So, can you pick the off with this topic? Will you pick the off? Yeah. So I'm going to move Is it working?
Hi.
Can I try? Hello. Is this working? Is it working now? How about now? Hello? Is it working? Yes. Can you stop this?
Check, 1, 2, 3. Check, 1, 2, 3.
Good. Cool. Okay. So I'm going to remove this microphone from here. It is very.
The clicker.
Okay, so this is your pointer. This is for next and previous slide.
Okay.
Use the laser also. If you press the thing in the middle.
Awesome.
So please just if you press this or this, then I have to come over and reset everything.
Okay.
So just back and forth and in the middle.
Okay. I might just use
Okay, yes. That
keyboard.
Yes, I do. Let's see this way.
Are you giving like time warnings or how is
Yes,
that
he's going to signal you.
Oh, okay.
What, are you signaling at 5?
Yeah, I should do 5 minutes.
Okay, is the total, what is the total time? Is it 20 or 15? Are you doing a total of 20 or 15?
Yeah, 15. Okay,
15 plus 5.
15, yeah, 15 plus 5. So I will tell you 5 minutes before finishing your 15.
Okay.
And then 3, 2, 1 before finishing your 5.
Okay.
Or meanwhile.
All right, sounds good.
There's a laser pointer in there.
Yeah. I think I'm good.
They don't have a HDMI. This one isn't working.
Do you want VGA to HDMI?
I also have my own laptop if that's easier.
We're ready?
I'm just gonna use that.
Yeah, you can. No, that's risky.
That's riskier.
If you go to other things, everybody online will see.
Okay.
Or the clicker.
Yeah, okay, cool, thanks.
All right, thanks everyone. Once again, this is a joint event from Intellect and AISC. Check out the booth if you want to know more about Intellect and these sessions being run frequently every week. I'm Mason, your host. Our next talk will be from Jenny Liu, Graph Normalization Flows. Let's thank the speaker and have her start.
All right, so today I'm going to be talking about graph normalizing flows, and this is joint work with several other people, Avril Kumar, Jimmy Ba, Jamie Kiros, and Kevin Swirsky. So there's this problem in machine learning of graph generation, and it's basically you have some set of graphs. So for example, you might have the two community graphs on the left here, or the protein graphs on the right. And given this set of graphs, you want to generate more graphs that look like they came from this set of graphs. So you want to generate similar looking graphs. And you can imagine that, that this has lots of useful applications in, say, drug discovery. So maybe you have this distribution over molecules that you know to be very useful as drugs. And now you want to figure out new candidates to test, and testing is kind of expensive. So to generate these candidates, you might say, I'm going to look at my current distribution of useful drugs that I know and try and generate molecules that look like these drugs. So in a lot of graph generation problems, you might have this distribution over, say, two community graphs, but the way the data actually looks is you're just given a set of adjacency matrices. So each training graph has an adjacency associated with it. And that's just this giant matrix where we put all of the nodes across the top and across this vertical column, as you can see on the bottom left here, and we just put a 1 for that entry if there's an edge from those two nodes connecting to each other in the graph, and a 0 if there isn't. So you can imagine that one way of solving the graph generation problem is to say, what if we had a set of node embeddings for each graph? So every node in the graph gets its own embedding, and we had some distance function that could reconstruct the adjacency matrix given these node embeddings. So it's sort of like you take this graph structure and you put it in like this high dimensional space and look at distances between the different nodes to figure out if they're connected or not. So if you had a set of such node embeddings, you could try and generate similar sets that look like your original training data. So in my talk, I'm going to answer two questions, which is how do we generate similar sets of node embeddings given some training data sets? And how do we actually, given just a bunch of adjacency matrices, find good node embeddings that can completely capture the structure of the graph just through the embeddings? So to answer the first question, I'm going to talk about this new model that we came up with, which is graph normalizing flows. But to get there, I'm going to take a bit of a detour and give a quick tutorial on normalizing flows and graph neural networks, which are two topics in machine learning that our work really builds heavily off of. So just to get a sense of how quickly I should go, how many of you here have heard of or are already pretty familiar with normalizing flows? Okay, and graph neural networks? Okay, cool. So let's start with normalizing flows. So there's a lot of math on this slide. I think it's probably going to be the mathiest slide, but the basic idea of a normalizing flow is that we're going to have a bunch of training data, and this training data in real-world applications in real life often has a very complicated distribution. It's not a distribution that you can easily sample from to get more data, and it's very difficult to capture this distribution. But there's this cool thing in statistics called the change of variables, which says that if you can find, which basically says you can find some function f that you can run on your training data, and that f will flow your training data to some space that we're going to call z. And this is a latent space. And the cool thing about z is that it's going to look a lot like a distribution that we can work with that's a lot easier to deal with, like a Gaussian. And basically, for the Gaussian, we already know its probability density function, so it's really easy to compute the probability of samples. And we also know how to draw samples from it so that we can generate things. So essentially, we're going to learn this function, which goes from our data to a Gaussian space at training time. And then if we want to basically generate more samples of our training data, we can sample from this latent space C, which is Gaussian, and then take this function and take the inverse and flow backwards into something that hopefully looks like it came from our training data. So I won't go into too many details, but you notice that I said we have to flow this thing backwards and take the inverse of our function. And it turns out that this is restrictive in the sense that it basically means that f has to be bijective. You need to be able to take its inverse. And there's a couple other restrictions having to do with the determinant of the Jacobian of f. And what this all boils down to is that designing f is actually a very interesting problem in machine learning that has been a pretty active area of research. And the particular formulation of normalizing flows that we focus on is called real MVP. And the way that they design f looks like this architecture above. So in their paper, they're trying to take distributions over images and generate more images that look like they came from that distribution. So they start by taking an image on the left and representing it as a real valued vector. So you just take all of the elements in the image and you just unfold them into this giant vector. And I won't go into too much detail, but basically what this architecture is doing is it's splitting that vector representing the image into two halves. So you see the blue and gray vectors on the left. And then it's running it through this architecture where at the end of the day, we're going to end up in this space on the right that looks like this giant vector basically gets transformed into something that looks Gaussian. And one really cool thing here is I said that this whole thing represents some function, right? And that function has all these restrictions on it. But if you look inside of this architecture, there are 4 circles that are pink and blue. Those 4 circles can be anything you want, even though this function is restricted. So because we're in the image domain, they use convolutional neural networks here. And once we get this function, once we're done training the network, we can then sample from the Gaussian space on the right here, run this whole thing backwards, and hopefully end up with more images of cute cats. So that's like a general overview of how normalizing flows work. The point is that you have complicated data, you're going to flow it to a distribution that you know something about, and that's going to help you do generation. So moving on to graph neural networks. The basic idea behind graph neural networks is that it is a type of architecture that makes learning on graph structured data easier because of certain inductive biases that it builds into the architecture. So let's say that we have this input graph on the left. And in this example, we're starting out with embedding vectors for the graph. So every single node gets its own embedding vector. That can be randomly generated, like say from Gaussian noise. It can be some property of the data set you have. Just for whatever reason, we have node embedding vectors. And now what we're going to do is we're going to run message passing steps. And a message passing step is like the central unit of computation in a graph neural network. So in the first message passing step, we'll focus as an example on this red node here. Basically, this red node is going to take in messages from all of its neighboring nodes shown in yellow, where the messages are the node embeddings of its neighbors. It's also going to take in a message from itself, which is just its own node embedding. And there's 2 main parts to a graph neural network. The first is the aggregation. So basically, if I'm the node, I'm going to look at all of these different embeddings and figure out some way to aggregate all of them. That can be like a sum function, or it can be like a much more complicated unit of computation. But however you want to do it, you basically come up with some aggregation of all of these different nodes. And then the second step is that you run that aggregation through a neural network, or an MLP. And what this is essentially doing is it's letting me figure out what is going on with the other nodes in the network. If I want to know like where exactly I am in space, compared to my neighbors, this is going to let me figure that out based on the information that my neighbors send me. The other thing to note is that node updates are synchronous. So at the same time that this red node on the top is updating itself, the other node on the bottom row here on the left is also getting updates from its neighbors. And this just happens all at once in one message passing step. And if we keep running message passing steps, eventually all of the nodes in the network will have propagated their embedding to all of the other nodes in the network. And you can just keep doing this as many times as you want. And if you take the node representations, the node embeddings, at the end of a certain number of message passing steps, the hope is that those node embeddings are going to be a lot more useful and a lot more representative of what that graph structure is like and the relationships between its items, its nodes, than when you started out. And you can take those nodes and you can use them for downstream tasks. Okay, I am going super slowly, so I'm going to have to speed up a little bit. Basically, we combine these two big ideas in our paper, which is on graph normalizing flows. And so I told you before that we have these flows that can take data and transform them to Gaussians. So now what we're going to do is we're going to take sets of node embeddings and transform those sets such that they look like they were draws from a random from a multivariate Gaussian. And so this is what our architecture looks like, and it's pretty similar to the real MVP architecture I showed you earlier, but there are some key differences. The first one, like I said, is we're starting with an input where we have a bunch of node embeddings for all the nodes on the left side, and we basically make it look like it's Gaussian at the output. And then the second difference is that these four functions that I told you could be anything, now they're going to be graph neural networks. Because in order for me to take all of these node embeddings in some structured training data space and make them look Gaussian at the end of the day, I'm going to need those nodes to communicate with each other to figure out how to configure themselves correctly. And so we're going to introduce graph neural networks in each four of these circles. And now if we want to generate a graph, we basically can sample a set of Gaussian vectors from the right and flow this whole thing backwards to get a set of node embeddings that hopefully represents something that looks like a graph when we're done running a distance function over it. So the last thing that I haven't told you is how we actually get these node embeddings, because as I said earlier, for these data sets, we're just given adjacency matrices. And the way that we're going to do that is to use a graph autoencoder. So we basically start with some adjacency matrix on the left, and we have some encoder that's a graph neural network that basically runs message passing over all of the different edges in our training graph. And it can basically find a set of node embeddings after doing all these message passing steps, such that if we use a really simple distance-based decoder that just looks at, say, like Euclidean distances in this high-dimensional node embedding space, we can then reconstruct the original adjacency matrix. And this is a diagram of our full architecture. So on the right, you'll see the graph autoencoder that I just talked about. So we encode the adjacency matrices into some space X, where that X is a really good set of nodes, where those sets represent the different training graphs. And then we can take that X and move over to the left and train the graph normalizing flow that I told you about to basically take those sets into Gaussian vectors. And then at generation time, we can run that from the bottom up to get a generated set that we can then run through our decoder, which is the simple distance function. So we ran a bunch of experiments comparing our model to this baseline called Graph-RNN. Graph-RNN is an autoregressive model that basically uses an RNN to decide at any given point whether or not to add a new node to the graph. And then once it adds a new node, it uses another RNN to decide which edges to add back to the existing nodes that it's already added. And so we experimented on two different data sets, one of these small 2 community graphs, and one of graphs that were actually drawn from like a real-world social network. And so you can see some of the samples here. So the left is the training data, the right is Graph-RNN, which is our baseline. The middle is Graph-RNN, which is our baseline, and the right is graph normalizing flows, which is our model. So for ego, it's kind of hard to tell the difference between the models and the actual training data because they all are doing a pretty good job. And then these are the results for community. Again, training data on the left, graph-RNN baseline in the middle, and us on the right. And so here our model is having a little bit more difficulty with like just spacing out the two communities correctly. So sometimes we get this like one giant connected community. And finally, we also ran some, I guess in generative modeling, it's like hard to get good quantitative evaluations of your models often, but you can basically, for the graph generation problem, run this script that looks at a bunch of different features of your graphs, like the degree or the orbit on the graph. And so we ran this script and found that our model is competitive with graph-RNN, but as you can see with community small, we still need some work. So here, smaller is better. And in terms of future work, in the graph-RNN paper, they ran their experiments on much larger graphs as well. So we're also working on that now to really test out how robust our model is. And you can also imagine that there are lots of other domains that have graphs, like in computer graphics, you have scene graphs, or you have like meshes that describe different objects. So one other thing that we're thinking would be cool is to apply this to those other domains. And if you're interested, here are a bunch of resources related to what I talked about. All right, thank you.
All right, any questions? Regarding getting the embeddings of the nodes and using the autoencoder, how does that network look like? Is it like typical autoencoder with one hidden layer and one output layer, or?
So you're talking about like this?
Yeah, string.
Yeah, so I guess like the encoder is a graph neural network.
Mm.
So we take like the input graph and then we just run a bunch of message passing steps. I think I probably forgot to mention like we start out with just like random Gaussian vectors. So like it's just really like noise at the start. And then like the graph neural network learns to transform that noise into like some set of embeddings that like when we run this decoder on it, it gets us the correct adjacency at the end.
And do you see any future perspective on interpretation of general neural networks? Because you can, I guess, pretty much visualize complex neural networks, and there is a huge consensus that neural networks are not very well interpreted. Mm-hmm. So that can this work increase or better explain future neural networks and then decrease the general concern in the public?
I mean, I guess like one thing you could maybe do is look at like in the intermediate message passing steps, like where do the node embeddings end up, and sort of figure out like what algorithm is it using to like correctly push this Gaussian noise into the right place. Like is it sort of like looking at like big picture structures first and then like pushing all of the like nodes within like each community, for instance, into the right place, or like I think if you just like look at the message passing steps, maybe that could be interpretable, but that's not something that we've looked at.
Yeah.
Describe how the decoder loss works in this case.
Oh yeah, so it's actually just like a really simple, I can like show you afterwards, but it's just you take the like L2 distance between the two norms, and then you run it through like a sigmoid that's like flipped along the y-axis, and that basically like thresholds it to 1 or 0. And I guess we use some thresholding rule where like if it's above 0.5, then it's 1. And
very good question. Which brings me back to another one. So it seems like you're utilizing this kind of cycle GAN idea, which I like. But how do we ensure exactly that first of all, what is, when you say the intelligent distribution is Gaussian, how do you define it? Second of all, how do you ensure that that representation is Gaussian? I mean, is that the premise of your DCN? Could you elaborate?
So I guess the thing that we're really trying to ensure is Gaussian is like this Z space at the end of the day looks like a set of like draws from a multivariate Gaussian. The way that we can ensure this is like it's sort of just it's like baked into the change of variables rule. Like that rule says that you can basically flow a complicated distribution to a Gaussian given some constraints on this function that you're using on your data distribution. So that's like basically just, it's like baked into our objective function, if that makes sense. Yeah.
So when you say affected the objective, do you also receive loss for it, or?
I mean, I guess we're taking
Because you're sampling.
like so the loss itself is ensuring that like we learn a function that correctly flows the data into a Gaussian.
Any other questions? All right, let's thank Jenny.
So much. Pick him up at all? From here? Yep. Which microphone? With this one? Hello, hello. Yeah. 1, 2, 3. Check. Good.
So this is for recording, not for.
Yes, that's for recording.
Is there any like loudspeaker?
Sorry?
So like
loudspeaker. I think this one works. Yeah, just to speak to this one for the room.
Okay.
This goes to your right pocket, if you have pockets. Excellent. And I can just put it on your.
So I have 15 minutes.
Thank you.
Do you have access to internet?
No.
No internet?
No.
What format is your slides with?
Keynote.
Laser pointer.
Okay.
The one in the middle. There you go.
Give you access to internet.
Oh, okay. Should I unplug this?
No. Oh, yes. Yes.
You want to?
Yes.
You want to have the slides? Is that?
No, but yeah. It's just a quick one. Could you open your browser and do you have, what's your email address?
That was.
Could you go to your email so I send myself an email?
No, I.
Okay, and could you go to internet site? So there you go. Yeah. And then put in the password. Are you connected? Come on. What's your name? So go to your email.
No.
You should have access to internet.
You could just
Use my laptop.
hope that you don't have this. Oh yeah.
What is the problem here?
You need to join this. You need to join Hangouts.
Can I send this to you later after this? It can be shown on the screen.
The issue is we're streaming this online, so you need to have access to internet. Can you export it in any other format?
Sure, sure.
Is that fine? Do you have any interactive slides?
Yes, I do. So that could be a problem.
Okay. So let's.
So what's the problem with are you using your hotspot?
I am, but it's not. Her browser isn't really. You got internet access, right?
Seems like, but I don't know what's the
Could
problem.
you go back to the browser? Yeah. Let's connect her to yours.
Just use my phone.
Is this a company website? Do you have another browser?
So I'll try to export it.
Yeah, can you just send us the PDF? Then you can just play it from your laptop. Oh, but you can't email either.
You have a USB key?
Do you have a USB key?
I don't have it.
Yes, hon? We don't have any.
Yeah, so that's why I wish to try it
we should have
before this.
tried it
Yeah.
before.
Oh,
You need your dongle.
I'm Luchin Tan from a company named RSVP.ai. Today I'm going to present a paper which is describing a deployed system developed for JD.com. And we are trying to detect a problem called customer complaint escalation. And we are using RNN with some manually extracted features. So let me first introduce RSVP.ai. We are a Canadian-based startup company. So we are located in Waterloo, and then we have other offices in China. And what we do here is we try to understand human language, understand all the natural language, and we build up different systems, try to teach the machine to learn and then to talk like a human being. And the company that we are working with at the time of the project is called JD.com. And JD.com is one of the largest e-commerce company in China. And we have a number here which says as the first quarter of 2018, the active user on the platform is over 300 million. So we are talking about the problem called customer complaint escalation. So we look at the problem first, start from example of the conversation between a customer service agent and a customer. So here, the agent started his conversation by a very common welcome sentence. Say, for example, I am agent number 1234 and I would like to help you. But actually, the customer has already had some emotion before starting the conversation, and he has getting annoyed by some problem. So he wished to solve the problem immediately. But what the customer agent did is he didn't solve the problem immediately, but he's trying to go through some common regular process. So the customer getting really annoyed, and then the customer started to threaten the customer service agent that I would like to protect my right, or like I would like to file to a higher level institution. I would like to file to the government and talk about some special issues, and then I would like to post my experience online, and I would like to talk to other customers. So this is a problem that comes more frequently nowadays. So all customers nowadays are expecting a high quality online shopping experience. Whenever during the shopping experience, the customer feels any dissatisfied on any aspect of his purchase, or he feels that his or her right getting violated during the whole experience, they would like to express their complaint. And the existence of the online chatting customer service and also the call center makes this expression more easier. So the customer would like to go online to talk with the customer agent, or will give a call to the call center, express this complaint. And then usually after they express this, they would like their problem getting solved immediately. But most of the time, the customer service agents are not doing a really great job. They don't solve the problem immediately. So some of the customers would like to go to a higher level authority, for example, the government, and then they would like to express this complaint to go to the higher level, which we call the customer complaint escalation. So we group these kind of customer into a special group. We call them tough to please customers. And this kind of customer, so as what I said, first they would like to connect to the company's representatives. So they contact the agents first. So as according to the statistics, about 75% of this kind of tough to please customers, they would like to talk with the agents online through chatting. And then about 25% of these kind of tough to please customers, they would like to give a call to the call center, or they will talk to the customer agents face to face. And then after that, they will go to the higher level for example, the CPB. And then we also counted the number that about 70% of these kind of customers connect to the agents first and then go to the higher level. And also there are about 30% of these tough to please customers, they didn't talk with the company's representatives. They go directly into the CPB. So what we are doing here is we are trying to detect this kind of special customers, detect those customers that has high risk of going into the higher level to express their complaints. And then what we can do is we can try to go through their dialogue history between the customer agent and the customer, and then try to detect from the 70%. So based on the numbers that given from JD.com, we know that there are more than 300 complaint customers every day to the highest level CPB in China. And then we know that the problem keeps going on. This kind of bad customer service experience will cause a huge damage to the company. Not only about the brand loyalty, but also about like the reputation online. So they really take this problem as a serious problem. But this is also a really hard problem because we are not we are not only detecting the sentiment of the customers, but we are actually detecting the intent of the customer, the real intent. Are they really going to go to express their complaint? So this is very different. Many customers, they say very bad word, they express their angry when they are communicating with the agent, but they are just threatening. They do not go to the higher level. So the ratio that between the real complaint customer and the overall customer is really a small number. And also why we say it's very important for a real-time detecting system, because we also counted that how many customers go to the higher level within a day after communicated with the customer agent. And also how many customers waited until about a week, about a month, and even longer time. So about half of the customers, after communicate with the agent or the representatives of the company, they will directly go to CPB to complain. And then about another 40% of the customers, they wait from 1 day to a week, so which means they wait within a week. And then another about 10%, they wait a month, and then about 4% of the customers wait more than a month. So we treat it as an online classification problem, and then we only do it over dialogues because we know that 75% of this kind of customers go through the online chatting, and also this is a very good starting point. So we can first solve the online chatting problem and then go into the phone calls, the call centers. So the numbers here that the real complaint customer over the overall customer number is lower than 0.01%, which means this is a very rare case. And then how to detect the real intent of these kind of customers. So we use a model. What kind of model should we use? So this is a NLP problem. So we started from very simple models. So we start from TF-IDF vectors. So if you know what is TF-IDF, it is something that can give you a number for each individual term and then tells you basically the importance of this term. So we start from using TF-IDF vectors, and then we go through into a even higher level abstract of the features. We do some manually engineered features, and then of course we tried neural networks. So we started our experiments from a published network. So this is called hierarchical attention network. So this is published in NACO 2016. And then, so this network has 2 different layers. So it extracts different information from the word level and the sentence level. So this is something that works, but when we tried our experiments, we figured out that the network here is too complicated and it didn't give more benefit to the real problem. So we simplified the model here. And then here is our model. So we take a fixed window size of the incoming dialog stream, and then we take the agent sentences with the customer sentences as the input of the model. We use bidirectional LSTM to extract some information between the words and the sentences, and then we also used attention mechanism. So this is a flat, we call it flat attention network, and then this is a baseline model of our experiment. So what we added in here is we added in some more features that we already proved that they worked. For example, like the TF-IDF vectors, we know that for many other NLP tasks, these are very good features. So we add them into our FNN, or we said flat attention network. And we also add in some other external features. So these external features are also like commonly used NLP features. For example, the emotion or emojis in the sentences, and then the use of different punctuations, special punctuations, for example, like question marks, and then how long is the sentence, how many words is used by the agent or by the customer. And also we collected 2 special dictionaries. These 2 special dictionaries are the common words that are used by the customers who going into the complaint process. So we counted the usage of these special terms. And then we combined everything together into the FAN full model. And then connect everything into a softmax layer, and then go to the classification. So this is our evaluation. We evaluated the model by using recall. So the recall is defined as the number of detected complaint customers in top K. So K here means that, for example, the company has a specialist pool that we report to this specialist pool, and then the specialist will try to connect to the complex cases of these customers and then try to solve their problems more efficiently. So the K depends on the size of the pool. And then we divide it by the number of customer complaints on that day. So we compare the different models. So we have some different baselines. The first baselines are the logistic regression or the like GBM, the tree algorithm, on some special vocabularies. And then we also tried some simple neural networks, for example, FastTaxi and LSTM. And then this is our FAN base model. So it beats all the baseline models. And also when we add into the TF-IDF, it gets even higher, boosted the performance. And the full model, which means we add into TF-IDF vectors and also the external features. So it is the best model that we tested. Also, because we noticed that this is a very rare case, which means we need to carefully select the size of the negative examples. For example, we take the complaint as a positive examples, and then we tested the different sizes of negative examples. So we figure out that until a certain race, there's no benefit to add into more negative examples. So we tested the model on history data, so it performs as about like 20 to 30% of the recall, and we also tested on a deployed system. So this is the online result, which means our model performed almost the same performance on the online. So here are some lessons we learned. So we always start from some simple models. We don't need to go into the most complex model. And then usually in some real online systems, the complex models, it means that it takes more time for training, it takes more time for the prediction, and usually it doesn't work for your online system. And then we don't always need to start over. We have some good features. We have some existing solutions. We can add into, we use those solutions. We add into our fancy models. And then the third one is, if your NN model cannot provide enough capability, you can always add into some manually extracted features. So yeah, this is the thing that I want to share today.
We have around 5 minutes. Oh no, we're over, right? That's 5 minutes per class. 5 minutes. But yeah. Okay. Let's have 5 minutes for any questions. I can get the questions started. So first, you showed us a few models. It seemed that when you added TF-IDF, there was a significant boost. Now, did the other models that weren't yours use TF-IDF as well, or?
So the thing that is the TF-IDF is just used for taking some for some special vocabularies, and all the other models, I didn't have enough time to mention that they are actually exactly using these kind of features.
Great, beautiful. Then the comparison is really fair. They've been using TF-IDF.
Yeah, they are using it, and we are using them.
Okay, beautiful. Any questions from the audience? Okay, I'll ask another one. There's another one. So you had it was recall at 5,000, was it?
Yeah, 5,000.
5,000. How did you come? Because you didn't show any F measures. It seems that it's not standard to show it, but we also do want to know how good or bad the model is performing on precision.
Precision, yes. So this is a very special case. So the company, they don't really care about the precision. So you can imagine that. So they want to cover as many cases as possible. So the recall is the real thing that they really care. They want to cover as many cases so they can waste their time to treat some negative cases, but they also solve the customer problems. So they don't really care about the precision. So that's why we only use recall.
I see. Okay, beautiful. At any point, does it get infeasible? Like 5,000 seems to be a feasible one. They're like
yeah. So this depends on the pool of the special customer service. So there is a special team that we report to this team, and then this 5,000 person can call individual customers to solve their problems. So they have this capability of 5,000. That's why we set it as 5,000.
Beautiful. Any questions from the audience? I'll ask one more question, and maybe if there's anything after, we can go home. So the next one, did you have? Could you show me the architecture, please? If you still have them on, otherwise.
Yeah.
Oh, yeah. Interesting. Okay.
Yeah, I should have a picture of the full view. There.
Alright. So, could you tell me? So there are dotted lines coming from W attention. Could you explain about that and how all the attention mechanisms kind of work together? To get the encoded dotted representation?
So this is a very typical attention mechanism. So the whole network is just the by LSTM added into the traditional attention mechanism. So there's nothing special here. So the dot here is just showing that. So this is actually the attention weights.
Okay, so let's. So what's W a subscore? So that's the weights of your attention, right?
Yes.
Where does it come from? That's not connected.
From the training, so we do back propagation and then update those weights.
Okay, gotcha. All right, beautiful. Any other questions? No, well, let's thank the speaker. Thank you very much.
Thank you.
It's a 20-minute break, I think. Or 15 at this point. Thank you so much.
Okay, we have a 15-minute break. Let's be here at 3. All right, welcome back, everybody. Simon is our next speaker. Please welcome him.
All right, so my name is Simon Kornblith. I'm a research scientist at Google Brain, and today I'm going to present our paper, Similarity of Neural Network Representations Revisited. This paper was previously presented at ICML this year, and it's joint work with Mohammed Nourouzi, Hong-Lak Lee, and Jeff Hinton. So the motivation behind this work is that it would really be great if we had a way to understand the representations of trained neural networks. So why trained neural networks? Why not just study learning algorithms? Well, so the problem is when we train a neural network, there's an interaction between the learning algorithm and some structured training data. We don't know the structure of the training data, so there's some limitation to what we can understand about how this trained neural network is going to act based on our knowledge of the learning algorithm alone. Ultimately, we need to study something that consists of both the learning algorithm and the data. And so one way to do that is to try to look inside the trained neural network. And so one approach to understanding a trained neural network is to look at its representations. And in particular, we can think about ways to compare the representations of the trained neural network. And this is an approach that has been very successful in neuroscience, which is what my background was originally in. So I want to start by introducing kind of what is a representation. So for the purpose of this work, when I say representation, what I really mean is a matrix. And the columns of this matrix are some set of features. So for example, responses of neurons in some layer of some neural network. And the rows of this matrix are examples. So we pass some data set through the neural network. We get the responses of all the neurons, we stack them up into a matrix, and this is our representation. So I also want to say, mathematically, it's simpler to think about this when you center these features, so when you subtract the mean across all the examples. So that's something that we do in all the math throughout this talk. So because we're comparing representations, we really need two matrices, X and Y, and these represent responses in layers maybe of the same neural network, maybe of different neural networks, but it's important that the examples here are aligned. So the number of rows in these two matrices is the same, and each row represents the same example, but the number of features can be totally different. There's no requirement for any kind of alignment between the neurons. So next, let's kind of think about what similarity means. So the simplest definition of similarity between vectors is just a dot product. But we also extend this idea to other kinds of inner products. So we can replace the dot product with positive semi-definite kernels. So now moving on to this idea of how to compare representations. The simplest way of comparing representations that we can think about is we just take every possible pairing of features between the two representations, and we just measure similarity between them. So we take their dot product. And if we do that, we get this matrix X transpose Y there on the right. But there's another way we could think kind of intuitively about comparing these representations, which is for each of these neural network layers, we can take the dot product between all possible pairs of features. So we can measure, all possible pairs of examples. So we measure similarity between the examples and not the features. And this gives us this examples by examples matrix XX transpose. It measures the inter-example similarities according to this neural network layer. So in machine learning, sometimes people call this a gram matrix. In neuroscience, we would call this a representational similarity matrix. So if we want to compare two of these representational similarity matrices, then the easiest way to do that is just reshape the representational similarity matrix into a vector, and then take its dot product with another reshaped representational similarity matrix. Yeah?
Is there kind of like a nice interpretation of X transpose? Because X transpose X is like the correlation between features, right? But this is correlation between individuals. Like,
yeah, so every element of this matrix is the dot product between one example and another example according to the neural network representation.
Like, I guess I'm asking, is that like meaningful in a way? Because like...
Okay, let's just have that question at the other side.
Oh, sorry.
Okay, yeah, I'm happy to return to it later.
Oh, yeah, sorry.
So it turns out that actually these two ideas are kind of the same thing. So comparing the features here, if we do it in a specific way, if we take the dot products between all possible pairings of features, we square them and then we sum them up, that's the same as taking the dot product between these two reshaped inner example similarity matrices. And to turn this into a similarity index, we want to normalize it. And the normalization does two things. First of all, it makes this invariant to isotropic scaling. So we don't want it to be the case that the similarity changes if we just make one of the representations bigger. And it also gives us a number between 0 and 1, which is convenient to think about. And it turns out we aren't the first people to come up with this idea. And actually, it's been rediscovered several times under several different names. So in the psychology literature, it's known as Tucker's congruence coefficient. And more recently, in the machine learning literature, kind of a generalization involving kernels has been named centered kernel alignment. And I want to talk a little bit more about how to get this generalization that uses a kernel in place of the dot product. So the idea is very simple. We have these representational similarity matrices, XX transpose and YY transpose, and we just replace those with centered kernel matrices, K tilde and L tilde. So basically, we take the kernel, we compute the kernel between all possible pairs of examples, that gives us a matrix, and then we center the rows and the columns of that matrix, and that's kind of equivalent to centering the features in the linear case. So having come up with this similarity index, the next question is, how do we know if it's any good? And this is actually like a very difficult question to answer because there's not really any single definition of similarity that makes sense for all problems. It's kind of like similarity can mean whatever you want it to mean, and really what matters is what you're going to use it for. One thing that we feel like is maybe the minimal thing that you can ask for a similarity index that you're using to compare neural network representations is if we have two neural networks that are architecturally identical, but they're trained from different random initializations. We want to take a layer from one network and measure its similarity with all the layers of the other network, and we want it to be the case that the most similar layer is the layer that actually corresponds architecturally. So in this example, if we take the third convolutional layer of a neural network, we want it to be more similar to the third convolutional layer of another neural network trained from a different random initialization than to any of the other layers of that network. And so we can actually perform this sanity check, and if we do this with the linear version of CKA, which is what I was showing you earlier, we get a plot that looks like this. So here, the x and y axes are the layers of two different neural networks that are architecturally identical, but trained from different random initializations. And brighter colors here indicate greater similarity. So you can see that the diagonal here is brighter than the off diagonals, and that indicates that the architecturally corresponding layers are more similar than the non-corresponding layers. So beyond this plain CNN that's trained on C410, we can also look at a ResNet trained on C410 and a transformer that's trained to perform English to German translation. And we can see that in each of these cases, CKA passes this sanity check. The diagonals here are brighter than the off diagonals, and we can recover the architectural correspondences based on similarity alone. We can also compare CKA to approaches that have previously been proposed to measure similarity between neural network representations. So here I show the similarity between layers using canonical correlation analysis and singular vector canonical correlation analysis, which are kind of ways of measuring similarity that have been used in previous work. And you can see here that you don't see this bright diagonal, and actually, like, a lot of the layers are very similar to either the first layer or the last layer of the network. And that kind of indicates that there are problems with these methods. And we can also take this sanity check and we can make it quantitative by saying, okay, we've got 10 neural networks trained from different random initializations. If we take all of the pairs and we take a layer from one and measure its similarity with all the layers from the other, how often is it that the layer with maximal similarity is the architecturally corresponding layer? And if we do that, you can see with CKA, we can recover the architectural correspondences with over 99% accuracy, but with these other previously proposed methods, the accuracy is much lower. And so you might be wondering, based on these results, what is canonical correlation analysis, And why have people proposed to use it previously to measure similarity between neural networks? And why does CKA seem to work so much better? And so mathematically, actually, there's a very nice relationship between canonical correlation analysis and CKA. So the idea behind canonical correlation analysis is that we compute this first CCA correlation by finding some linear combination of the features from X and linear combination of features from Y such that their correlation is maximized. And the number that comes out of that is this first CCA correlation. We can compute further CCA correlations by doing exactly the same thing with the restriction that these new linear combinations of features have to be orthogonal to the previous linear combinations of features. So that's how CCA works. It turns out to get a similarity index from CCA, you can sum up the squared CCA correlations and divide by the total number of CCA correlations, which is the number of features in the smaller representation. And if you do that, it's equivalent to taking the dot product between all possible pairings of principal components of X and Y, with the principal components normalized to unit length, and then again dividing by the number of features in the smaller representation. So you can already see that this looks kind of like CKA, but we can also write CKA in terms of the normalized principal components, the eigenvectors of XX transpose and YY transpose. And if we do that, you can see that the main difference is that in CKA, we're weighting the dot products by the amount of variance explained by the principal components. So CKA is placing greater emphasis on similarity between these components that are responsible for more variance in the original representation. So that's all the math for this talk, but I have a few more kind of interesting empirical results to show you. So the first thing is that we can use CKA to measure similarity between architectures, between different architectures. So here on the left, I have neural networks with different numbers of layers. So a neural network with 8 convolutional layers, 10 total layers, and a neural network with 18 total layers or 16 convolutional layers. And you can see that if you measure similarity, it's kind of like in the deeper network, the new layers are inserted in between the old layers in terms of what their representations look like. And you see there's still a diagonal in this plot, even though the 18-layer network has twice as many layers. On the right, I'm measuring similarity between a 10-layer plain CNN and a 14-layer ResNet. And again, you can see that there's some architectural similarity between the two networks. So finally, we have this kind of serendipitous finding of that kind of demonstrates what CKA can tell us about what goes wrong when we train a neural network and it doesn't behave as we expected. So we have this 10-layer CNN with 8 convolutional layers, and it gets 94.1% on CFAR10. If we make it twice as deep, then it gets 95% on CFAR10. So this is kind of the typical deep learning story. You just make it deeper and the accuracy goes up. But the problem is if you make it 4 times deeper or 8 times deeper, the accuracy actually goes down. And so you could try to explain this in terms of like maybe there are vanishing gradients, maybe there's something wrong with the training, but you can also just directly look inside the trained neural network and see what's gone wrong. And so if we measure CK this time between layers of a single trained network in each of these plots, so we no longer are using pairs trained with different random initializations, now it's just one network, you can kind of see what's gone wrong in these really deep networks. So if you look at the 2 layers, or the 2 networks on the left, you can see that the representations are kind of iteratively refined throughout the network, and each layer is really only similar to the layers directly around it. But these deeper networks, which actually have lower accuracy, you can see that there are entire chunks of the network that all have very similar representations. And we can verify that CK actually gives us an accurate idea of how the neural network operates by training a logistic regression classifier on each of these layers individually to perform the original classification task. And if you do that, you really do see that in that very deep network on the right, the accuracy plateaus less than halfway through the network, suggesting that there really is no meaningful refinement of the representation happening in that second half of the network. So that's all I have for today. Thanks for listening to the talk. And if you're interested in code or in reading the paper, you can go to our website, ck-similarity.github.io. Thanks.
Amazing. Yes, please follow up. Could you ask a question again so that we're back in the context?
Oh yeah, sure. I guess yeah. I'm sorry, I might have missed the beginning, but I think you were motivating something as we want to find the correlation between examples in the training set as opposed to correlation between features.
Yeah. So actually, I think this is the slide where you asked the question.
Yeah.
So you can think about how do we measure the similarity between the representations of two examples, and then you can think about like maybe we can compare representations by measuring similarity of similarities between examples rather than doing something explicitly in feature space. And so that's the idea behind this method, but it ends up being the same thing as just measuring similarity in the original feature space, at least if you're doing it with the dot product.
And this metric for similarity that you developed, I guess like it's just one possible metric, right?
Yeah.
Okay.
Yeah, so especially like if you go back to the slide with a bunch of math. So if you look at CKA there, you can imagine like there are different possible weightings of the dot products between the principal components there. And there's actually like one way to come up with a similarity index with different weightings is to use regularized CCA instead of CCA or CK. And we actually show that that kind of interpolates between the two in the paper.
Thanks.
Does the problem of deeper networks disappear if you use ResNet, the residual layers?
Yeah, so we actually have a 56-layer ResNet in the paper, and it doesn't have this problem. Like, it doesn't have this issue of having entire blocks of the network where the representation is the same. Yeah.
So one example is like we have a training model, but you actually want to quantize the parameter to get the fixed point model.
Yeah.
So the statistics is different, right?
Yeah.
So in that, did you do the experiment for that case?
So we haven't tried working with quantized networks. I mean, everything here is just with off-the-shelf standard real-valued CNNs.
Oh, I see.
If you go back to the representations that you had for transformer versus where you showed the diagonal, it's an interesting, the contrast seems very interesting. Do you have an intuition as to why? So the resonance, you seem to have that maybe we can guess. You seem to have a wider sort of diagonal, maybe because it's propagating information back. But I just wanted to know if you had any, especially for transformer, why is it more dispersed?
Yeah, so we have so both transformer and the ResNet have residual connections. And for transformer, you can also see that there's kind of this funny pattern where every other layer is similar. And the reason for that is that in the transformer, the architecture alternates between these like self-attention and feed-forward network sublayers. And you can see that the self-attention layers are similar to other self-attention layers, and the feed-forward network layers are similar to other feed-forward network layers, but there's less similarity even between adjacent feed-forward network and self-attention sublayers.
Can we say then that walking through depth, transformer networks are less distinct from each other, the layers are less distinct from each other in that sense?
Yeah, maybe. I mean, I think that's true of all residual networks. Like, at least if you measure them with this similarity index, you kind of see that there's not as much refinement if you use the representation after the residual connection.
And a dumb question. So you had you showed accuracy for the measures, but is it because the number of so it's always balanced because the number of features and examples are always balanced?
Which slide?
So when this one, yes. So the issue usually with accuracy in normal machine learning tasks is that if it's imbalanced, it doesn't really reflect the performance.
Yeah.
Over here, everything seems to be balanced. Is it because is that why?
Yeah, so we're measuring accuracy of these different methods on the same set of CNNs. So we train 10 CNNs for different random initializations, and then we just apply all of these methods to that set of CNNs.
Any other questions there?
Can you go back to the diagram? So yeah, like I guess in the first one, I guess the similarity between the self-similarity between like layer 7, I think, and like layer 8 and layer 9, they seem like low in comparison to the previous layers.
Yeah.
But don't you like norm everything? So wouldn't it be the same? Or
so I can kind of tell you the explanation for why that is. Basically, when you have two different architecturally identical networks trained from different random initializations, it kind of seems like as you go through the network, the representations become more dissimilar. And the reason for that seems to be that, like, so I can tell you one way to fix this, which is if you make the networks really wide, then all of the layers end up being very similar to each other. So it seems kind of like there are differences between the different initializations that accumulate over the layers.
Okay, so like a narrow and deep network is expected to have kind of like divergent similarity.
Yeah.
Like short and wide would probably be.
Yeah.
Okay.
Thanks for the question. Oh, did you have? Let's kind of fun. We'll move into the other talk. Let's thank Simon. Thank you very much. Two to 3 minutes before the next talk.
Thanks.
Thank you so much.
Thank you. Oh, thanks.
I got it.
Amir, the bucket.
So, questions from audience. There's one audience.
There's no magic between this network. We can use this network to kind of develop some idea of what
Just time.
So this is the mic for online, this is the mic for here. This is more important. Okay. Yeah. All right. Are we ready? Are we live?
Yeah.
All right. Michael is our next speaker. Let's welcome him.
So I'm just going to get started. So I'm going to present work on the look-ahead optimizer. This is joint work with my great collaborators, James Lucas, Jeff Hinton, and Jimmy Bach. So I guess just quick check, how familiar are we with optimization? Like, who has heard of Atom before? Okay, cool. So yeah, we'll just go through some related work. So a lot of work on optimization has been on like adapting momentum or like changing how fast you train on different directions. But another perspective you can take is on like averaging the weights you accumulate throughout training. So this has actually been studied from the perspective of convex optimization back in 1992 by Polyak, and Rupert had some work in 1988 as well. So essentially what the work from before showed is that if you take the arithmetic average of your weights, you get faster convergence in convex optimization.
Technical issue?
Yeah.
Could you put up this for a second? Okay. Is it okay if you only see the slides over there?
Sure.
Yeah, that's fine. Let me see.
Yeah.
Oh, sorry, that's not yours. That's right.
Yep, that's right.
All right. So. All right. Could you just recap quickly?
Sure. Yeah. Okay. So while weight averaging has been studied in convex optimization, people haven't really looked at it more carefully in neural networks until more recently. And one example of this is stochastic weight averaging, which comes from a group from CMU in 2018. So the idea of this is you also just train a neural network randomly, but you can sort of create an ensemble effect by averaging the weights you obtain at different points in training. You average those weights in weight space, and then using that model, you can get lower test error and just do better generally. So this shows that even in like deep neural network space, averaging weights tends to get you to a region of like lower loss surface, of lower like test error. And we'll sort of see this sort of visualization come up in our work as well. And one other work that I'll briefly mention is people have looked at trying to find like what's like the sort of best weight, average weights, by trying to find a position where the gradient is 0, because that corresponds to either a minima or a saddle point. And you can do this by solving a system of linear equations based on your past iterates. However, this takes more memory, which is like k, the number of iterates you consider, and like by the length of the your neural network, which could be millions of parameters. So I'll just dive into our method, which sort of relates to the previous work that's been done. So going back to like a Hinton paper from the 90s, we'll refer to our weights as the fast weights and the slow weights. So we have some initial point here, which we cache, and then we take steps using an inner optimizer, such as stochastic gradient descent or ATOM. And this might take us to a few different positions in parameter space. So after we take a set number of steps, for example, 5 steps, what we do is we look at the point we started at, the slow weight that we cached, and then we take a step in this higher order direction generated by taking multiple steps of the inner optimizer. So in this case, this is this particular direction, and we, instead of going all the way to where we have stepped, we go like something like 0.5 or 0.8 of the weight instead. So we get to this position here. And then from this position, we again cache the point, take more steps of the inner optimizer, such as ATOM. We end up at a new point, and then this is our new search direction. So our next update is in this direction, and then we repeat the process from the orange point again. You can write this out in pseudocode as well, where the thetas correspond to like the fast weights and the slow weights, and this sort of just falls into the paradigm of nested loop optimization that has seen resurgence lately. All right, so that's the method. We'll go on into another way to visualize this method. So this sort of gives a bit of intuition on why look-ahead tends to work well, which we'll see occurs in a wide variety of domains. So again, we start from our starting point here, and we take k steps. This is using stochastic gradient descent. And what you'll notice is that if you interpolate along this direction between the first and last iterates, you get to a region of higher test accuracy. And you also actually turn out to have lower training loss and higher train accuracy as well. So all the metrics you care about, you tend to do better by doing this sort of interpolation. And we can show that you can continue along the trajectory of SGD. You'll still end up on the outside, whereas if you do another look-ahead step, you end up at a region of even higher accuracy. The way we generated this plot is you take 3 points in parameter space, which might be like 5 million parameters. And what we do is we define a plane using these 3 points. So you can define a plane by subtracting these 2 points and then projecting everything onto that first dimension. And then the second component is subtract this point from this point in this high dimensional space, subtract the components that's explained by the first one, and then you have like a 2D way to visualize your weights in high dimension. So this might lead to some artifacts because of the projection, but in general, you can see that like along this direction, we tend to get to a region of higher test accuracy. So to explain like more mathematically why this works, we can look at the noisy quadratic analysis. This has been a model used sort of as a easier way to explain phenomena that occur in deep neural network optimization, since it's typically hard to analyze that directly. So there's a lot of good work from like James Martins, Roger Gross, Tony Wu, and Guodong on the noisy quadratic model. And essentially the way this model works is we assume a quadratic model of the loss where thetas are parameters. And instead of getting the true gradient, which would be AI theta I here, we get a noisy version along each dimension. So we get AI theta I plus CI, where CI is drawn from a normal Gaussian distribution. So this sort of models like the stochasticity from like training your model, and it does a good job of explaining effects of batch size, which like recent work from Guodong has shown that the effects of batch size are well explained by this model. So this is the model we use for our analytical analysis. So using this model, what you can do is you can compute the variance of look-ahead and vanilla gradient descent after like some number of updates. And what you find is that the fixed point variance of look-ahead is always lower than that of SGD, because this first term here is less than 1. You can plot this on the noisy quadratic model as well, and you see that even with different choices of alpha, we tend to converge to a region of lower loss. So on the simple quadratic model, it checks out. We'll turn now to empirical results on a variety of different domains. So the first setting is CFAR 10, to explain these experiments, what we do is we optimize for the inner loop optimizers, such as stochastic gradient descent here. We find the best hyperparameters for stochastic gradient descent, and then we use those settings and then tune the choices of K and alpha for look ahead. So just a quick reminder, I guess, K and alpha correspond to how many steps we take with the inner loop optimizer, and alpha is the amount we step in the direction. So these are the two additional hyperparameters we introduced. So if you do this procedure, you can see on CFAR 10, look ahead performs best in terms of reducing the training loss. And we can actually show a variety of different things, such as robustness to hyperparameters. So in the case where you change the inner loop optimizer, such as SGD, and like you say you picked a bad learning rate, you can see that even with a variety of different learning rates, look ahead still performs much better. So across a broader range of hyperparameter settings, you still can recover better performance than just using SGD itself. We can do this with momentum as well, so you observe a similar effect. And one other thing is, one complaint you might have is we're introducing K and alpha, which are two additional hyperparameters that you have to tune. But as this experiment shows, if you try different choices of K and alpha, you still get better performance than the SGD baseline, which is shown in blue. You can see that the other choices of look-ahead parameters do better than the SGD. Yeah. And one other intuition to mention here is that what we can actually do is we can plot the accuracy or the loss of each point along the slow weight, fast weight trajectory. So when we do this, we see that the fast weights tend to degrade the test accuracy, and then when you do the interpolation step, you get restored to a region of higher test accuracy. And this effect is even more drastic right after a learning rate decay. Here you can see that generally the fast weight, the slow weights just restore the previous performance. And this matches with the intuition from the noisy quadratic model earlier, where we showed that look ahead reduces the variance and hence is more likely to be at a point of better accuracy. We can also do this with by scaling it to ImageNet, which is a huge image classification data set with over 1 million training images. And we train a model that has 25 million parameters. You can see that look ahead converges faster. We picked a learning rate schedule. So the one that goes here with the dotted dash line, that's like the traditional one used by most people in computer vision. But we found that like look ahead performance like plateaus much earlier. So this suggests that you can even decay your learning rate faster. So you get this waterfall effect earlier and you get to a region of higher accuracy faster than you would before. So I guess one thing here is that we use the learning rate schedules that people have used for like SGD or Atom, and we don't like specifically tune them for our optimizer. That's like a potential direction for future work. This also scales to ResNet 152 as well with like little tuning. You just change it. You just change ResNet 50 to 152 and you still get the faster convergence effect. And we can see that not only do you get faster convergence, but typically generalization tends to improve a bit as well. So like look ahead generalizes pretty well on both image data sets. On neural machine translation with the transformer models, we actually also see slightly faster convergence. The final performance is more or less the same. But here this highlights that you can also use Atom as an inner loop optimizer and you still get really good performance. And finally on Penn Tree Bank, here we wrap look ahead around both SGD and Atom. And you can see that we actually dominate the perplexity curve with the solid line and get almost like versus the baseline, we get higher test perplexity by almost 2 perplexity points, which is pretty significant.
That's a language model.
Yeah, this is a language modeling task. So to summarize, this is a new algorithm that gives you better convergence on a variety of different tasks with little hyperparameter tuning. So in the context of having a new data set which you're unsure about, this could be a good thing to try because You can just throw it in there, and you don't need to tune hyperparameters so much, and you can get faster convergence. This is due to the reduced variance effect we explained earlier, and I guess in terms of extensions, we can sort of look into learning rate scheduling and a whole family of methods that maintain memory information. So here we maintain one additional copy of the parameters. You can sort of imagine different ways of updating that copy. And finally, if you want to use look ahead, it's 2 lines to incorporate into your existing code. You have an existing optimizer, and then you just need to add an if condition where you set your alpha and steps, and we have code online as well. So yeah, this paper will be at NeurIPS 2019 in a few months. I'm happy to take questions.
Beautiful. Let's thank Michael quickly. We have time for 1 or 2 questions.
Do you, so you update in the internal loop, you update as if regular SGD, right? Yeah. After you pass a few number of steps, then you determine the direction that you want to update.
Yeah, exactly. The inner loop, you just use exactly SGD. Like we don't do any, we just use SGD in the loop.
Have you encountered any problem, or did you try to specify different activation function when you try this method?
We mainly use like the value activation, I guess, because for these benchmarks, there's typically like an architecture and like training procedure people follow, and we just keep that fixed and then like change the optimizer.
So there is no need to shift to a different activation function, like nothing?
No, yeah, we don't need to change anything else.
So you attribute most of the performance improvement to variance reduction. If we did full batch gradient descent instead of stochastic, do you expect the results to still hold?
Yeah, I think that's a tricky question because there's like a lot of papers arguing about large batch versus small batch. So it's hard to say. Like, it's possible that stochasticity is important in getting you into a place that generalizes well as well. So like, I think our results like hold for the SGD setting, so it's hard to extrapolate to full batch. Yeah.
So very quickly with the last question, is the intuition behind this is that you kind of reduce the variance in between batches, and in some way, I think empirically you also showed that it's similar to momentum in some ways. Is that, what are your thoughts on that?
Yeah, I think that's generally true. Like, you might think that you're reducing overfitting to each specific mini batch, like in the plot I showed where accuracy can degrade quite significantly, because you're incorporating like more information before you actually take an update.
Super. Let's thank Michael. Thank you very much. One second.
Because you don't need to backdrop, we're just like, yeah, after you're updating 8 times, you just all do so in all our experiments, we run like k times 4 updates on all the.
Is it still?
No, I said like that SGD takes 200 steps, we only do 100.
This is your pointer, and back and forth. And if you press in the middle, but just don't press these two. It's going to take you out of this window. All right, our next speaker is Shauki. Let's welcome him. He's going to talk about eigen damage, structured pruning in the Kronecker factored eigen basis. Let's welcome him.
Okay. Hello. Hello, everyone. Today I'm going to present our paper on neural network pruning, titled "Eigen Damage Structure Pruning in the Kronecker Factor Eigen Basis." So why we need a pruning? The motivation. There are several motivations from different perspectives. The first one is that from the biological perspective, that human beings at the birth usually have very less neurons and connections, and it will grow gradually at a peak around 6 years old, and then it will gradually reduce. The second perspective is from the generalization perspective, that people have shown that pruning can be used to improve the generalization error bound, which means that we can improve the generalization performance with pruning. The third one is the most important one, that is also the most practical one. People in nowadays are interested in deploying large models on mobile devices. But we know that those devices are battery constrained, and the large models cannot be directly deployed. And pruning is a way to reduce the model size while still maintain the performance. Specifically, there are two main categories of pruning. The first one is weight level pruning, which proves the weights of the neural network or the connections between the neurons. The problem with pruning is that it will result in irregular sparsity in the resulting weight matrices. So this is not so GPU friendly. And for structure pruning, it proves the neurons or the channels. As a result, this maintains the convolutional structure, and that is more GPU friendly. And our paper is focused on the structure pruning. Yeah. So we focused on Hessian-based pruning method because it has several advantages. The most important one is that it only requires us to specify a pruning ratio, and then it will determine the neural network architecture automatically. And for Hessian-based method, it basically relies on the following approximation, which is the Taylor expansion around the local minima theta star. Because we are around the local minima, so the first order term is 0. And if we drop the higher order terms, the only term matters is this quadratic term. Actually, it's the Hessian of the neural network. This approximation mainly tells us how remove one weight will affect the training error. So we will prefer to remove those weights that will least increase the training error. For Hessian-based methods, there are two very representative methods. The first one is the optimal brain damage. The second one is the optimal brain surgery, the OBD and OBS. These two methods differ in their usage of the Hessian matrix. The OBD uses a diagonal approximation to the Hessian matrix, so it is much cheaper to compute. But the problem is this is not very accurate because it ignores the correlations between the weights. Whereas OBS uses the full Hessian matrix for accounting the correlation, so this is more accurate. But we know that computing the exact Hessian is almost intractable for larger networks. So this limits the usage of the OBS in practice. Equation 2 and 3 is the pruning criteria of OBD and OBS. So this is the criteria for deciding the importance of each weight. So it's easy to show that OBS is better than OBD if we prove weights one by one. That means we need to recompute the Hessian matrix for each iteration. So this is very expensive. Like if we prove like a network with millions of weights, that means we need to compute the Hessian matrix for millions of times. This is intractable for practice. So in practice, we will prove multiple weights at a time. So that means we compute the Hessian matrix and we prove a certain amount of the weights with the computed Hessian. So we would like to ask the following question: that if we prove more than one weight at a time, is OBS always better than OBD? At the first glance, the answer may be yes, because OBS uses more computation and it uses the full Hessian. So it should be better than OBD. But it turns out that the answer is no. Let's look at this very toy example. Suppose we have a neural network only has 3 weights, which is 1, 1, 1, and the corresponding Hessian matrix looks like this. This basically tells us that the first 2 weights are highly correlated, and the third weight is roughly independent to the first 2 weights. So for the first case of pruning one weight at a time, then we can show that OBS is better because OBS will prove either the first or the second weight because those 2 are redundant to each other. But OBD will prove the third weight. As a result, OBS makes less increase in the error, which is 0.01, but for OBD it's much larger. For the second case, if we prove 2 weights at a time, as a result, this time OBD is better because for OBS it proves the first 2 weights, which it thinks regards these 2 weights are highly redundant. But the problem is that if we remove these 2 weights simultaneously, then no other weights can compensate their roles in the neural network. So as a result, OBS makes a larger increase in the error. So this is basically saying that there are 2 problems of OBD and OBS for if we prove more than one weight at a time. The problem of OBD is very clear. It ignores the correlations between weights, so it's not good. For OBS, it basically makes incorrect conditioning because it decides the importance of each weight condition on the existence of all other weights. But if we prove more than one weight, some weights in the theta minus I will also be proved. So this condition is incorrect. So in summary, we can say that OBD and OBS, they use the diagonal Hessian and the diagonal Hessian inverse for pruning, and as a result, these 2 methods fail to capture the correct correlations if we prove more than one weight. So how to solve this problem? This is what our paper trying to solve. But we propose that we can do pruning in a new coordinate system, and in this system, coordinate system, all the weights are closer to independent. That means there's no correlations between weights. So we can use whatever pruning algorithm in this space. And also in this space, the OBD and OBS are equivalent because there are no correlations between weights. So ideally, this space should be the eigenbasis of the Hessian. But there are 2 issues needed to be addressed if we want to do this. The first issue that is because the Hessian is intractable, so compute the eigenbasis of the Hessian is also intractable. And also, if we want to map the original weight into a new space, we need to introduce the extra parameters, which is the new eigenbasis. So for solving the first problem, we adopted the facial matrix to approximate the Hessian. This is very commonly adopted in the literature, and the facial matrix is defined as the covariance of the gradient. So it has the same shape as the Hessian matrix, so it is still very large. So that means we are still not able to compute the exact facial matrix. But for the facial matrix, we have very accurate and efficient approximation, which is the k-factor approximation. The main idea of the k-factor approximation is that we can decompose the facial matrix of a neural network into the chronic product of two small matrices. So you can think of this as the out product of two matrix. Yeah. So basically, DS is the gradient to the pre-activation, and the A is the activation. So this is thing that we can use this chronic product to approximate the facial matrix. The computation is almost linear to the size of S and A if we do quadratical. Yeah. So lastly, we define the KFE. This is the basis in which we do pruning. If we do eigen decomposition to the S and A, we can finally decompose the approximated facial matrix in this form. And this is the KFE, which in place of the eigenbasis of the Hessian matrix. So yeah, so this is the basis in which we do pruning. And this gives our pruning algorithm. So suppose for the original layer is a 3x3 convolution, which has an input channel with 512, and the output channel is also 512. And we first map the weights into the KFE by the following equation. And as a result, it will decompose this layer into a 3-layer bottleneck structure. And then we do pruning in this space by pruning either each row or column of the weight matrices. And then we map the weight back to the original space. So yeah, so our first experiment is to verify that in the KFE, the weights are almost independent to each other. So we visualize the facial matrix in the original weight space and in the KFE. We can see that in the KFE, the facial matrix is closer to almost a diagonal, showing that the weights are uncorrelated to each other. Whereas in the original weight space, these weights are highly coupled, showing that the KFE the correlations are captured in the KFE. So this is showing that the network after pruning by different methods. So those networks are not being fine-tuned. So we can see that the network pruned by eigendamage achieves much lower error than other methods. So that means pruning in the KFE is more accurate. And the next result is that one-pass pruning, that we specify a pruning ratio, and we prune such amount of weights in a single pass. And we can see the red curve is our method. We can see that this achieves significantly better results than other methods. So, and because for Hessian-based methods relies on the Taylor expansion, so this is only accurate around the neighbor of the local minima. So if we prune too many weights at a time, this may be not very accurate. So we use the iterative pruning. That means we do pruning for a small amount of weights at a time, and then fine-tune the network, and then prune, then fine-tune, doing this cycle iteratively. We can see that in the iterative setting, we can obtain much more accurate results than previous. And also, our method performs much better than other baselines. So we found that we can further reduce the model size by decompose the weight tensor of the middle layer by this way. As a result, we can drop the off-diagonal off-diagonal terms, only keep those diagonal terms, but we need to introduce two new bases, which is U and V. But we found that U and V can be merged into the KFE. So that means we can reduce the size of the middle layer without without need introduce extra parameters. So this is the results of comparing with the depth-wise separable. The red curve is with the depth-wise separable. The green curve is our method without depth-wise separable. We can see that with the depth-wise separable decomposition, the performance can be further boosted. Yeah, that's basically our paper. Any questions?
Take a few questions. All right. No questions. I don't have any either.
Okay.
Could you show the results?
Wait, which one?
Yeah.
This one?
I could come up with any either. Could you give us a little bit of a background on pruning per se? Is it is the idea that if you perform any sort of pruning, the network performance would increase if you do it the right way? And is it?
If we prune only a small, like 20% of the weight, then hopefully we can improve the performance compared to the dense network. But if we prune more and more weights, then the performance may hurt, but it's not a lot.
I see. Is there a premise that by having a smaller network, if you can maximize it to also increase the performance? Is this?
Yeah. There's some workers they trying to design a very compact network, but in general, their performance is not as good as the large network, because to optimize for those small networks, it's very difficult. And also,
So, when doing the pruning, do you need to do the retraining the network?
Yeah, we need to. Oh, yeah. Yeah, so we need to first train the network until it converges. So we are at a local.
Can you compare the converge time with the different method?
You mean after pruning?
Yeah.
In our paper, we have compared the conversion.
It's difficult or it's easier?
I mean, if your pruning algorithm is more accurate, then it's easier because, like it's showing this figure. Yeah, this figure. If your pruning algorithm is good enough, then prune 80% of the width, there's no increase in the training error. So that means you start at a very low error, then less epochs needed to fine-tune the network. For other methods, after pruning, they perform almost as random.
Can I ask a quick question for the Hessian matrix in the example? The 3x3 you gave.
Which one?
I think the previous slide. Yeah, this one. So you said the entries are correlations as well?
Yeah.
So then for the third, for A33 or H33, why is it 0.5? Shouldn't the correlation be 1 for the weight with itself? Oh, in H, yeah.
Which one?
Yeah, the third diagonal on there.
Oh, this one?
0.5. Yeah.
This is a diagonal, so it means that the variance of that parameter.
Oh, okay, right.
This terms are the off diagonal, so terms capture the correlation.
Okay, yeah. And then is the pruning layer by layer or for the entire structure?
So in our experiment, we just specify a pruning ratio, and then it will choose to prune how many weights at each layer or channels at each layer.
Oh, it's so it's for the entire network.
Yes.
Oh.
Yeah, but for our approximation, we use the layer-wise approximation, not the hashing for the entire network.
But the results are comparable.
Yes, the results is fairly comparable because the correlation between different layers is very small. And the people use a block diagonal facial matrix to approximate the for facial matrix is very accurate.
There aren't any other questions? Let's thank the speaker.
You remember what the format was? Should we just be PowerPoint? And I just wait 5 minutes for 5 minutes.
Yeah, like okay.
You sure you sent it to me? I'm sorry, I can't see it. No, but is it events or event? Events. This? Yeah. Emily. It's this there. Do you have notes you want to read from? I'll have it on my laptop. Okay. If you press this will jump out. Okay. I'll press this. Okay.
Tawaki, take it away. Let's go first.
Hey guys, I'm Tawaki and I'm an undergraduate student at the University of Waterloo. Today I'll be presenting our work on semantic segmentation that I worked on as an intern at NVIDIA. So our paper, Gated SCNN, recently got accepted at ICCV19, an international computer vision conference in Seoul. And we also recently released our code base to the public for anyone who is interested in using our work. So for those who are unfamiliar, the problem we work on is semantic segmentation. Semantic segmentation is essentially pixel-wise classification that is done on the image. This is a very challenging problem with a wide array of applications in robotics, commerce, autonomous driving, and more. So a lot of people actually ask me when I'm working on this problem, aren't like segmentation networks already good enough? So the answer to that is that existing segmentation networks are definitely good, but they can definitely be also better. So the two main categories of failure cases that we will focus on is a loss of detail at high distances and also noisy boundaries. So on the left image, we see that objects at higher distances, like the poles in the background, and smaller objects like traffic lights and poles suffer greatly. This is not good because for applications like autonomous driving especially, we need to be able to see stuff at high distances to safely stop, especially at higher speeds. On the right image, we see that the network, even with fine label ground truth, fails to predict accurate boundaries. This is especially apparently in small classes like traffic lights in orange and poles in gray. Even for the easy classes like cars, you can see that the boundaries actually seem a bit unstable. For the traffic lights, you can't really even tell that those are actually traffic lights just based on the shapes that they have. So why exactly do these problems exist? Shouldn't these mega networks basically be able to learn these things? So one of the problems that these networks have is that they significantly overfit the texture. According to a study done at a conference paper at iClear, they basically discovered that while humans are really good at determining the class of objects based on their shapes, neural networks are not. For an example, in this image of a cat, humans are able to tell that the picture on the right is still a picture of a cat, just with a different texture. Meanwhile, the neural network completely fails in this experiment and instead actually performed better at humans at classifying textures. Consequently, most of our segmentation models are initialized with something like ImageNet and likely suffer the same type of issues. This explains why segmentation networks fail at higher distances because farther away and smaller objects rely more on shape rather than texture because the textures get obfuscated at low resolutions as it goes farther away. Another problem that these state-of-the-art networks has is that they downsample the images heavily. For these segmentation networks to make accurate predictions, it needs to increase the spatial receptive field of the convolutions to capture larger portions of the image. This is particularly important for large objects in the image. By downsampling the image, the effective receptive field increases without having to increase the size of convolutions, which would take more memory and compute. Some negative side effects of this is that high resolution details are lost. This should be at least part of the reason why farther away objects tend to perform worse, just because the textures become obfuscated with downsampling and that the boundaries are noisy because the boundaries are kind of lost in the downsampling process. There are tricks to mitigate this, but eventually not enough. And post-processing methods exist to improve this kind of stuff, but they are definitely slow. So basically what this tells us is that we need higher resolution features for image segmentation. So to summarize, we came up with two solutions to solve this issue. First, we want to focus on shape. And second, we also want to focus on using high resolution features. So we'll go ahead and make something that does both. So this is what a typical DeepLab V3 Plus architecture, which is one of the state-of-the-art architectures in segmentation, looks like. It has a cascading feature extractor, which then gets fed into a multi-scale feature extractor, the ASVP, and that's it. We propose that we basically add another branch to this network to force that branch of the network to process shapes, using edge detection or boundary detection as a proxy for shape processing. We can fuse those features with the regular features for our spinal segmentation. And this is our proposed architecture. And basically, we use what we call gating mechanisms to facilitate the cooperation between the regular branch and the newly added shape branch, such that that outputs the boundaries. These gates help to keep the shape stream lightweight because it takes a lot of the features from the regular branch. And we can go ahead and take a look at what these gates look like. So these gates basically learn to focus on certain features. For an example, we see that gate 1 highlights the relatively low-level edges that include the edges on textures, whereas gate 2 focuses a little bit more on the high-level boundaries. We can see here that our network does learn shapes through the boundaries, and the boundaries seem consistent and clean even for smaller objects farther away in distance, as well as thin objects like poles. These high-resolution and high-density feature maps help to guide our network to produce segmentation maps with better boundaries. Let's also take a look at the actual boundary outputs. So we can see here that the actual boundary outputs, and the edges actually seem very stable, even temporarily, and looks very nice even for hard object classes like bikes and poles. And you can especially see that on poles because even across frames. So now that we have boundary outputs, how do we actually use them to better guide our segmentation network? So we propose what we call a dual task loss, which enforces consistency between the two representations we learned in our two-stream network. We can then look at our resulting segmentation mass, which is the result of fusing the two branches. So the dual task loss consists of two different loss terms, which enforces bidirectional consistency. I don't want to focus too much on the specifics here, but I just wanted to include this in case anybody is curious about the actual formulation. Also added a key here just to make the variables and corresponding representations a little bit more clear. So our first dual task loss term consists of taking the spatial derivative of both the ground truth boundaries and the segmentation mass boundaries, which we then constrain using the absolute loss term. And for our second dual task loss term consists of taking the standard cost entropy loss term on segmentation and adding more weighting on the pixels where we have a high boundary confidence. We basically just do this by using a simple indicator function with thresholds our boundary output. And these loss terms help to produce our final outputs here. We can see here that the final output of the segmentation mass, as well as the corresponding edges for these segmentation masks. And it's kind of hard to see on this projector, but hopefully you can see that the boundaries look a little bit more cleaner than they were before.
We're comparing this with any other thing that we've seen before, or the comparison is with...
This one's specifically with our work. This is all our work, yeah. Just different video frames that we show the edges and also the segmentation of. And these edges here are produced from the segmentation masks that we actually produce. So here's another area of visualization of our methods. Wherever it's not black is basically where the network makes a misclassification. We can see that our network significantly improves on areas that dflat v3+ makes, especially on borders. So you can see an example for like the third from the left one. You can see some people walking. Yeah, I think there's some people. Yeah, and you can see that the areas on the people actually decrease, especially on the boundaries. So how do we actually do quantitatively? We identified two problems, so we also proposed two different metrics for our two problems. So for high distances, we propose what we call a crop mean intersection over union, which is actually just an intersection over union on the segmentation mass calculated at different crop distances. The higher, the farther away in the image. And this works particularly well as a metric for distance in our case, because in our outdoor scenes, typically the center of the image corresponds to farther away objects. Here we can see that in the strictest regime at 400 crop, we get close to a 6% upgrade in mean intersection over union. We can also see that the quality of mass for dflat v3+ decreases at a much faster rate than in ours with distance. So we can see that our network is more robust to distance than compared to dflat v3+. Second, we also have the boundary evaluation. So we compute this by first converting our semantic segmentation predictions to an edge map, and then comparing against ground truth edges by using precision over recall per class. We also evaluate this at different thresholds, which gives different slack in the evaluation process. So we see here at the strictest regime at 3 pixels, we get close to a 4% upgrade. This also means that our boundaries are in fact much better aligned than dflat. And so we covered our two main metrics, but we don't want to forget about our main metric, which is just the primary metric, which is mean intersection over union on the actual segmentation mass. And we see here that even in our classical evaluation scheme, we get close to a 2% upgraded mean intersection over union on the cities case validation set. And that pretty much covers our work. Thanks for listening.
Any pressing question? Okay, I did want you to, could you kind of look at, so if I want to summarize it, there were two main approaches. So we wanted to increase the focus on the shape rather than texture. And the other one was trying to deal with the distance
with the downsampling.
With the downsampling, so the resolution of the images.
Yeah, so we have like high resolution features that we use to guide our segmentation.
Could you do a quick recap as how, so are those the solution crop? I just want to quickly, if you could remind me of the solutions. So crop, MIOU, and boundary F-score, are these the solutions, or these are?
So these are just two metrics to define whether or not we actually solve the problems that we propose in our paper.
Could you do a quick recap as to both solutions? Because we did see the results, which was impressive.
Oh, so you mean like what that network actually does?
Yeah.
So the main thing here is that you have a second branch that outputs the actual boundaries. And then these boundaries are high resolution features. So they're actually processed at the maximum resolution that the input images come in. But we can keep it lightweight because they're boundaries. So they only have a finite number of, channels, right? Or feature channels. Whereas compared to like the regular stream, if you wanted to keep those high resolution features, at maximum you might have like 4,096 channels, which at high resolution would be super heavy. But in our case, we can keep our memory consumption low while keeping the features to be high resolution because we convert them into boundaries, which are like, a single channel output.
So is that what the shape stream does then?
Yeah, so it's basically outputs a boundary, which is supervised on the ground truth boundaries.
Gotcha. And the fusion module will basically fuse both.
Yeah, the consistency between them.
Beautiful.
So what this does is basically it learns boundaries as a proxy of shape, and then also does that at high resolution because that's possible with edges because it's low numbers of channels.
Very few number of pixels as compared to the entire image.
And I didn't put it in the presentation, but in the paper we also show how many parameters it increases by, but it only increases the base architecture by very small amounts of parameters.
That's surprising. Because if it's just like 1 pixel, it's not going to scale by resolution.
Yeah.
Any other question at the moment? Okay, I'll ask mine. So you have a few gates. Did you play with it seems you put them in a specific place in between different sort of resolutions, so the number of channels increase and the resolution decreases. Is there any intuition as to why that takes that shape, or if you increase the number of gates, would it be any better?
So there's, I guess, a finite number of gates that we can use, but this is mostly empirically determined how many numbers of gates is optimal, basically.
From the range of probably 1 or 2.
So like for each layer in the ResNet, you can put a gate on there, right? So we can only up to have like, say, like 5 or 7 or something. But in this case, we just use 3. And we see that we get pretty good results with just 3, so we want to keep it lightweight.
So then I guess what you're saying is that in this one, this is a 5-layer, the regular CN is a 5-layer.
Yeah, so this is just a ResNet-based architecture.
Right, and you're gating on just 3 of the layers. And so that was part of the empirical thing to where, not just how many gates to use, but where to place them. Okay.
Yeah. Cool. But usually like these ResNet architectures have a very low number of layers. So usually you can just like pretty much just figure out you want the first one probably and the last one and somewhere in the middle, right?
And somewhere in the middle. Okay, yeah, no, that makes sense. Okay, I see that. That's cool. It's very clever, man.
Very good question.
Does it would have the code posted online?
Oh yeah, so we have the, I think I put it at the very beginning. Yeah, all the code is there. Okay. So you can visit our project webpage and see our code and also our paper and stuff like that.
Sure. Any other questions from the audience? go home 10 minutes early. Well, there are exhibitions going on, so if you want to stay, feel free to. Let's thank Walker.
Thank you.